So last week, if you guys remember, we talked about groups. We said that there are some, specific properties we need to form groups. So we said that we have to have a set of elements. There is an operation. Whatever member we take from this element, and then if we apply that operation, the result that we get should be another element in this set. And then we should have identity group, identity element, and then we should have inverse and then associative rule. So these are the basics that we can form a group. So, the basic group that we know is integer, and then the operation is plus. So we saw that we could, having this all properties, we were able to, do some computation. And then we spent some time last week to see when we talk about Zn, this should be the set of integer mod sum n. So what is the meaning of that? So we had an example of mod 5, so Z5. And then you see that what we've done was that when we are talking about a group of mod 5 or mod n, so what we are doing basically is partitioning the set Z into some residue classes. And then the property that we got was that, no matter if we are looking into one residue class, and then we have some nice property that, these two elements, any of these two elements within the same set are congruent to each other, meaning that, if you take 5 or 10 mod 5, and then the remainder would be 0. So that was, the meaning of, congruent over here. So that's what we learned last week. So let's expand what we've just done a little bit more. So now that we know what is a group, what are the properties that we are looking for, let's look a little bit in a different topic of, suppose that I give you two groups, G1 and G2, and then we want to compare these two groups, right? You're not only always working with one group, there are many groups out there. And then we want to understand how can we make connection between two groups. So let me begin this that he calls homomorphism with an example. Suppose I have an infinite group. And this group is the set Z integers and the operation is plus. We know that this would form a group. And then we have another group that is a finite group. So the difference between infinite was that the number of the elements in this group is infinity. When we are talking about the finite group, we have a fixed amount of elements in this group. So let's talk about the group of mod 2, and then the operation is plus. So this means the set of integers mod 2. That's what the notation says. So with that, it means that we have a fixed set of integers that mod 2, whatever integer we take, we calculate mod 2. Basically, the remainder would be always 0 or 1. And then the operation is addition. So now, given these two groups, let me also write down this. So we are interested to understand if there is any similarity between these two groups. Anyone want to guess if there is any way that these two groups are related to one another? It looks a bit odd, right? So I'm talking about a set that it has infinite, elements, and then I have another set that it has only 2 elements. The only thing similar that you could see between these two groups is that the operation is similar. But do you think, the question is that, do you think that these two groups are way more than similar what it looks like to be, even though the group definitions are very different? So maybe this is a bit a difficult question. So let me give you a hint. So we have the set of integers. So I can say that the set of integers, I can break it down to the set of even numbers, right? and then union by set of all odd numbers, right? If you look into this set, we have positive and negative integers, and I can break them down into evens and odds, right? So maybe now we are getting close to understand what is going on. So let's see the operation on this group. So in this group, since we have these two elements and I have addition mod 2, so let me write down all possible scenarios. So if I have 0 plus 0, this is going to be 0 mod 2, right? If I take 1, I add 0 to it, it would become 1 mod 2. If I take 1 plus 0, 0 plus 1, again I get 1 mod 2. And if I get 1, I add it to itself, then the remainder to 0 would be, the remainder to 2 would be 0, right? So this is the entire operation that I have in this finite group. So now if I write down the logic over here, then you will start to understand the similarity between these groups. So if I take an even value, any even value from the set, and I add it to, I take another even value and I add two even values, then the result would be even, right? 2 plus 4 is 6, all of them are even. If I take an even number and I take another odd number from here, when I add them together, then the result would be odd, right? Or similarly, if I take an odd number first and I add an even to it, then again the result would be an odd number. And if I have an odd number and I add another odd number to it, then the result would be even, right? Can you guys see the similarity now? So it looks like that we can do one thing. We can map these elements to the other elements in this group. So I can do a map. For any even number, I map this one to 0. And if the number is odd, I map it to 1, right? So now we can see that if you want to add two even number, so even we would replace whatever even number you choose, I replace it with 0. And when we add these two things, the result would be 0, which means that it is going to be even, right? So it is interesting, right? So a group that is infinite, we don't have any restriction on the elements, and the operation is addition. With just a slight modification, you see that these two groups are sort of similar to one another. So, mathematically, if we want to do this, define this similarity formally, what we can say is that we can define a function f that take an element from this group Z and map it to this group Z2. And whatever that means, that if you take any even number, I'll map it to 0. And if you give me any odd number, I'll map it to 1. And that is it. So it means that I can correlate one group to the other group, right? And that became sort of interesting. So there are some similarity between these two groups in terms of, a sort of operation. And the whole magic was that when we divide the set of elements into even and odds, and then we see that when we add even and odds number to each other, there is a correlation with that, with the numbers that we do, addition on mod 2. So they are doing something similar. So somebody could ask, what about the other way around? Can we map from there to here? Is it possible? So let's see. Do you think this is possible? If I take any value over here, can I map it back to here? It looks like that is impossible, right? Because over here we have a set of integers, and over here all the numbers that I have is 0 and 1. So how do we show that? So I think it's a small proof. So we can say that the inverse does not exist. So to show that, we suppose that G, so that there is such a function G that can map from Z2 to the Z. Okay, suppose we have this function. So this means that G on given input 0, it should, mod 2, it should map it to some X, value in this set Z. And again, G on 1 mod 2, it should map it to some, integer Y. And let's just see why it cannot exist. So suppose that, whenever we see 0, we map it to some X, any integer. So from the operation on this group, we know that 0 plus 0 should equal to 0 mod 2. But, now that we say that for any 0, this function G, it would map it to some random X. So we say that X plus X is equal to X because we map 0 to X, right? From this property, mod 2. So the only value that can satisfy this equation is that X has to be 0, right? So that's how we formally show that it is not possible. But I think we don't even have to go through this proof. It is intuitively, and it's very easy to see that we can't find any function because, the domain and the range of this group is only 0 and 1, and we can't map it to something that, a bigger group. So things are missing. So it was a smallest example to see that, there are some tools that we can compare the group to each other. So this was just like to warm up. I want to discuss another property that it would become handy in cryptography. So let's see another group. So suppose I'm talking to the Z4, and then the operation is addition. And I want to compare this group with another group that the elements are 1, minus 1, I, and minus I. And then the operation in this group is multiplication. Okay, so let's see the correlation between these two groups. So in group theory, we have a table that called I forgot the name of this group, this table. Let's wait, maybe I will remember it. Anyways, so in this group, I think you are familiar with this group. So we would start to write down the elements of this group, 2 and 3. So we are talking about Z4, so we have mod 4. So it means that this would be the set of all values or all elements in this group. And then we start to, do the operation. So 0 plus 0 mod 4 is going to be 0. It's going to be 1, 2, and 3. The first thing doesn't really change anything. So because we add 0 to any element. So 1 plus 1 mod 4, it is just 2. 1 plus 2 mod 4, it is 3. 1 plus 3 mod 4, it's going to be 0. And then similarly, we can, do this computation to fill out this group. And 1 and 2, okay? So given this, okay, so we would do the same thing. We want to go through all the possible, results for this group. So I write it down, 1, I, minus 1, and then I, and then again 1, I, minus 1, and I, minus I. So let's do this results over here. So the operation is multiplication. So 1 times 1 is just like 1, it is I, it is minus 1, and it is I. The same thing repeats. Oh, I think it should be minus I, sorry. And over here also everything repeats itself. So it is just multiplying 1. So I times I, we know that it would become minus 1. I times minus 1, it would become minus I. And then I times minus I, it is going to be 1. And over here, we would similarly fill this table on I, it would become minus 1. All right, let me draw your attention to some interesting thing between these two tables. Look at these ones over here. So let's find all the ones over here and compare it to the corresponding location on the other table. So it looks like that well, all the ones are exactly mapped to the same location on the other table when we do this operation, right? Also, we can look into another operation. For example, look at the zeros. So I draw a line underneath. So location of the zeros. So I have 1, right? It is 1. This is 1 again, and this is 1, right? So it looks like that we have a very interesting property over here. So that I can map the elements from one group to the other group. So I define the function f from this group to be element 0. I'll map it to 1, right? Element 1, let me see what it mapped to. 1 is mapped to I. And then 2, it is mapped to -1. And then 3 is mapped to -I, right? And then similarly, we can now define our function g that does the reverse, connection. So element 1 here from this group can be mapped to element 0 from the other group. Element -1 can be mapped to element 2 over here. And then element I is mapped to 1, and -I could map to 3, right? In fact, these two groups, even though they have the same different operation, they only have this equal amount of elements. But with that, we see that there is more than just similarity between these two. In fact, we can map from one group to the other group, and then we can also map back from this group back to the Z4. And this is very interesting group, and this is a specific property that we call it isomorphic. So why is this important? Why did I bring it up for cryptography? So we are going to use this property of this group. So it looks like that operation on this group is addition, and operation over this group is multiplication. So the hunch is that if I want to multiply these numbers, I know that the multiplication, the computational complexity for multiplication operation is much more expensive than addition. So because of this property over here, if I want to do, let me give you an example. Suppose I want to do -1 multiplied to -I, right, in this group over here. So that means that I can use the function g to map these elements to the elements of the first group, the Z4. So based on this definition, -1 is mapped to 2, and then -I is also mapped to 3. And then I know that now I can, add 2 plus 3 in this group. So I can just do that addition in this first group. And then the result would be what? If I add 2, I add 3, the result would be 1. And then I can map this element 1, using f back to the g. So the result would be I. So let's see. If I do -1 times -I, the result would be I, right? And exactly what I got. But the trick was that I didn't have to do multiplication operation over here, which was way more expensive. Given that f and g are a polynomial or some optimal function that I can run them very quickly, then you see that I can skip the expensive operation in one group, and because of this specific relationship between these two that it calls isomorphic, I can basically go back and enjoy a fast computation on the other group. And no matter what of these elements I take and I do the computation, I can always get this result, right? So this is why I brought up this topic, and you can imagine that, sometimes if we can map from one group to the other group, then we can have a better performance. And this is the sort of property that we are going to use very soon in some group to see how we can do things a bit more efficiently. Okay, so I think this is all I wanted, most of the thing that I wanted you guys to understand from algebra. So I think we start with the definition of the how do we find a group, and then we practice why these things are important, and then we gave a lot of example that when you do a Zn, what actually you do with the set Z, and then we also have intuition how we can compare two groups when you're given at any moment. Now you have the tool to compare them. So let's go back and work on some other principles that we need now for public key cryptography. So from now on, we are going to suppose that we have two integers. We have a and b, and I think a lot of these things are quite familiar for you guys. I would just give you an example to remember. I suppose that a, b are integers and n is a positive integer. And then we have a notation that says a divides b. That it means that, for example, we know that 2 divides 4, right? Means that 2 is a divisor of 4. Or 3 divides 15, right? 3 times 5 is 15. But sometimes we also use this notation. 8 does not divide 15, because there's no way that 8 can divide 15. So 8 is not a divisor of 15. We have another notation called GCD. I remember, I think you guys are familiar with this notation of greatest common divisor. So let me give you an example for that. So sometimes we are interested to find the GCD of two numbers. For example, I ask you what is the GCD of 9 and 15, right? So you will say that 9 is 3 times 3 and 15 is 3 times 5. The greatest common divisor is 3, right? So the GCD is 3 over here. Or if I ask you what is the GCD of, let's say, 30 and 35, then I can say that 30 is 2 times 3 times 5, and 35 is 5 times 7. So you see that the greatest common divisor over here is 5, okay? So that being said, sometimes we have some integers that we call them relatively prime with each other. For example, the example that I brought here, 8, we said does not divide 15, right? We say that 8, because it does not divide 15, the relationship between 8 and 15 is that A is co-prime to 15, and the symbol is like something like this one. Or another way to say that, the GCD of 8 and 15 is basically 1, right? So if I want to do this computation, 8 is 2 to the power 3, and 15 is 3 times 5. So you see that there is no common divisor between them except 1, right? If I multiply 1 to both sides, so the greatest common divisor is 1. And that means that these two values, they cannot, one is not the divisor of the other one. And that is going to be very important for us. We will get back to this very soon. So we have another formula that we said that sometimes we are interested to find the factorization of some, integer n. And then we said that this is the generic form. So for example, if I asked you what is the factorization of 15, you can say it is, if you want to follow this format, we can say it is 3 to the 1 multiplied to 5 to the power 1, right? Or if I ask you what is the, factorization for 2 to 50, then you can say that, well, this is 2 times 3 to the 2 multiplied to 5 to the 3, right? So this is my P1, this is my P2, and this is my P3, right? So different primes, the basis of the prime. And then I can have, some different powers over here. So given that, then we would end up with a very interesting function called Euler function. In order to understand this function, let me give you some background. Suppose that I define a set called Sn, And the set n is all integer x such that x is greater than equal to x less than n, is between 1 to n, and x is co-prime to n. This means like the GCD of x and n is basically 1, right? As we define. So given this, this is very interesting set, right? So I'm looking for, like given this integer n, what I'm trying to do is to find all the other integers between 1, which is less than n, let's say, all positive integers less than n that are co-prime to n. So let me give you an example. Suppose we are talking about group Z15. So my n here is 15. And the Z15 is a set of all integers from 1, 2, 3, all, I'm sorry, 0, 1, 2, 3, all the way to 14, right? And then if I want to define the S of 15, what happens is that this is going to be only those integers that are co-prime to n. So 1 is the GCD of 1 and 15 is 1, is correct. 2 is co-prime to 15. 3 is not because 3 can divide 15. So 4 is, right? And then 5 is not, 6 is not, then 7, then 8, then 11, 13, and then 14. So only these elements are co-prime, and this would be the set. So if you look, the length of this set 15, how many elements do I have over here? If you count them, you find them to be 8. So sometimes we are interested that, given this set n, how many elements are in this set Zn, Z15, for example, that are co-prime to 15. And that number is defined by some specific function called Euler function. And this is the definition of the Euler function. So how does it work? Suppose we have the integer, the factorization of that integer, then using this factorization, then I can compute this phi function very quickly. Suppose, for example, phi of, if I want to compute it again, so phi of 15, I know that 15 is what? 3 times 5, right? So according to this definition, is going to be 3 minus 1 times 5 minus 1, right? So this is going to be 2 times 4, exactly the 8 value that I was looking for. So you see that you've seen this phi n, I've used it in RSA. So now you understand what does the phi n means. It just simply says how many elements are in set that are co-prime to this number. So that would bring us over here. I think we already understand what is, two values that are congruent to each other. It means that they are in the same residue class. But we can also show that we can say that they are n is the divisor of them. So let me give you an example. Suppose that 15 is congruent to 6 mod 3, right? So these two elements are congruent to each other because their divisor is just 0. So now I can say that 3 can divide 15 minus 6, right? So this is what it says. And the other definition that congruent residue is that when we are given some, A mod n, this is the reminder, then we can rewrite this formula in this format. And in the beginning, it might sound like this is not something very useful, but soon you will see that we're going to use this relationship to compute the GCD. But for some that they forgot this floor function, the floor function definition is that, for example, if I pass 1.2, the floor function would just return 1. And if I give like minus 2.2, then this function would return minus 3, right? So now if I ask you, I know that 17 mod 3 becomes 2. The remainder is 2, right? Because 3 times 5 is 15, and then the remainder is just 2. So according to this relationship, I can say that 2 equals to 15 minus the A, which is my 17, divided by 3 times 3, right? Then I can show that this is actually equal to 17 minus 17 divided by 3 is 5.3 times 3. And this is going to be 17 minus 5 times 3, right? Which is going to be equal to 2. So just different representation. Soon we will get back to this, and we will see that why this property is important and why did we bring it up. So in terms of later on, we want to do some operations. Just a small FYI that sometimes, when you want to add two numbers, A and B, add or, subtract them, we don't have to do A mod n and then plus B mod n and then compute the n mod n again over both of them. We can just directly add and subtract them and just compute the mod n. So you don't have to do these two operations. Seems to be redundant. And similarly, when you want to do multiplication, so you don't have to apply the mod n to A and B, before you multiply them. You can just directly multiply them and then apply mod n. Sometimes it happens that we have some equations, and then when you have B and C that are congruent to each other, so you add or subtract some constant integer A. So when that happens, you see that you can just basically cancel the effect, just like any other equation that you always work with. You can imagine this congruency to be like equality, so just cancel both sides, and you can just say B is congruent to C mod n. But there is something that you should always be careful when we are talking about multiplication. The only time that we can cancel a constant from both sides of the equation is that this A is prime, relatively prime to n. And the reason for that, soon we will practice that. You will see that if this is the condition, then there is a multiplicative inverse of A mod n, which means that there is another element C that when you multiply to A mod n, the result becomes 1. And only at that condition, you can cancel A from both sides. To make it clear, let me give you an example. Let's say I do 4 times 8. I would say this is congruent to 4 times 5 mod 6, right? If you check both sides, you will find that this is the case. So if you just blindly cancel these two, what you get is 8 is congruent to 5 mod 6. But is it the case? So 8 mod 6 is, we say that 8 mod 6 is the remainder is 2, and then 5 mod 6, the remainder is just 5, right? And these two values are not equal to each other. And this implies that 8 cannot be congruent to 5 mod n, mod 6, right? So this is an example to show you that it is not always the case that these two values always become congruent to one another. So that is given. I think here we are just spending some time to give some definitions. So soon things would turn to be a bit more interesting. So let's begin by two very, very interesting things that we are going to use a lot in cryptography. And that is, how do we find the GCD of two integer A and B efficiently? That is the first problem that we are going to address here. And then the second one is that we can, whenever we are computing this GCD, we can always find some integer, r and s, doesn't have to be positive, could be negative, that we can form an equation so that, r times a plus s times b, it would equal to the GCD of a and b. This is very important in cryptography. So I'm going to show you how we can do this GCD computation very efficiently, and then we will see some examples very soon. All right. So we are not going to prove. I'm just going to show you how do we do the computation. I think this is the goal for our course. The proof of the GCD is not very important for us, but there is a story that GCD of A and B, whenever you're computing this is equal to the GCD of B and A mod B. Okay. So given this fact, then we are going to see that how we can leverage this to do the computation, to compute the GCD for any two integer in a very quick time. So we say that for A and B, we suppose that they are some integers in a set Z, and so that A is greater than B and B is greater than 0. Okay, this is a condition. So I'm going to define two variables, and then you will see why. It would help me to write down the equations in a better format. So I'm going to define R0 to be A, and then I'm going to define R1 to be B. Okay. So remember from modular arithmetic and the divisor of two values A and B, I can rewrite this formula of R0. I can rewrite it as Q1 times R1 plus some R2, right? We just discussed about this issue, this equation, and always R2 is always smaller than R1. Okay. I will give you a numerical example. You will see that soon. Just bear with me to see the relationship. Then I can basically, using this fact over here on the top, then I can write down that I can now say R1 equals to some Q2 R2 plus some R3. So this comes here and this goes there. And then again, for some R3 to be smaller than R2. And again, I can continue this until I get to somewhere called RK minus 1 equals to QK, and then RK plus RK minus RK plus 1. And then for some RK plus 1 to be less than RK. And then this can again continue if you are very unfortunate to Rn minus 2 equals to Qn minus 1 Rn minus 1 plus Rn for some Rn again less than Rn minus 1. And finally, we would get to somewhere that Rn minus 1 equals to Qn times Rn plus Rn plus 1, where this Rn plus 1 equals to this thing equals to 0 at some point. So we would keep writing this relationship between these two R values, and until we get to somewhere that the remainder becomes 0. And if that is the case, we go back and we take this one as the result of GCD of R0 and R1. Okay, this sounds a bit odd, so let's go and write an example. I think that will really help. Suppose A is 48 and B is 18. and I'm interested to compute their GCD. So I'm going to define the bigger one to be R0, so 48. R1, I'm going to define it as 18. So let's write it down. I can say 48 equals to 2 times R1, which is 18, plus 12, right? Where we see that 12 is between 0 and 18. And we continue to the next one. This is not 0 yet. We continue. So I bring 18 here. And then I'll say that 18 equals to 1 times 12 plus 6, right? And 6 is something between 0 and 12. And I continue. So you see that this comes here, this comes here. See the relationship. And then I go, and at the end, I say that 12 equals to, right? So the 6 comes here. It becomes 2 times 6 plus 0, right? And we get to 0, we halt here, and then we go back and we say that this is, this was how the relationship. And then I go back and I say that GCD of 48 and 18 is actually equal to 6, right? So it is just like, writing this relationship and continuing down here. And that would help me to quickly find the GCD of two numbers. Sometimes in cryptography, we are, not sometimes, most of the time we are interested in computing the GCD of two values that are co-prime. So in this case, for example, we talk about 8 and 15. So let's say what happens. So I can say that 15 equals to 1 times 8 plus 7, where 7 is greater than 0 and less than 8. And then I can say that 8, right, equals to 1 times 7 plus 1, right? And I can say that 7 equals to, again, 1 times 7 plus 0, right? So we get to 0, we go back, and this is the GCD. So it says that the GCD of 15 and 8 is going to be 1, right? This is their common divisor. So it looks like that this is very interesting, and with some small logic, we can quickly find the GCD of any two integers using this formula. And in fact, this is one of the most efficient ways to do this computation. And if you see our fact up here, every time that we divide A mod B, so we kind of drop one of the bits of A. So if you look at this algorithm at the end, the order is a log n, where n is the number of the bits of, for representing A. And in fact, this is very interesting, and this would help us to find these GCDs very efficiently. So this would drive us to some even more interesting formula, and that is going to be the, we want to change this algorithm a little bit so that we can find the multiplicative inverses. And the algorithm called extended Euclidean algorithm. So remember, we need to find some integer R and S in Z such that R times A plus, suppose we want to find the GCD of A and B again, R times A plus S times B equal to the GCD of A and B, okay? So now the goal is basically to find this integer R and S, not just to find the GCD. In order to find this, again, I write you the mathematical formula, then I will go to an example and it would become clear just for you to see the rhythm. So when we find the, from the previous page, when we get to over here, that we find this, latest formula that I got the GCD, I would start to work out from here. and I would rewrite these formulas all the way up to get to the first formula. So that is why we call it extended algorithm. So the latest one, I have Rn equals to Rn minus 2 minus Qn minus 1 times Rn minus 1. And then you can write this one as, Rn minus 2, and then we can do Qn minus 1, and then we go to Rn minus 2 minus Qn minus 2 times Rn minus 2, and all the way up, right? So we continue all the way until we get to some expression A plus some expression B. And these are going to be your A and B. Let me give you an example. I think this mathematical notation makes it a bit hard to understand. Remember when we wrote the GCD of 14 and 18? So we said 48 equals to 2 times 18 plus 12, right? And I said 18 equals to 1 times 12 plus 6, right? So the GCD says that, when you find this was the 6 was the GCD of 48 and 18. So I will start from the last equation, and I would the only thing that I do, I treat these numbers as variables. I don't do multiplication or anything, and see how the magic would happen. So I can write that 6 from this latest equation. I can say that 6 equals to 18 minus 1 times 12, right? I'm just, rearranging the formula. Okay. So over here, I have this 12, right? So you always get, some equation at the end, some value at the end. So we have that value on the previous formula. So this 12, I can rewrite it as 48 minus 2 times 18, right? So I can say that this equals to 18 minus 1 is nothing. So 12, I can write 12 from this equation. It is 48 minus 2 times 18, right? Let me just be very concrete with this. So minus 1 times this, that you would see the 1 over here. So then it means that I can say this is equals to 18. I just do the multiplication, 18 plus minus 48, right? Plus 2 times 18. This is what I get from there, right? So now you see that I have a common factor over here. So I get a factor from 18. So it would become what I would get. I would get 18. From the first one, it would be 1. Plus from the second one, 2 times 18, I would just get 2. Plus minus 48, right? Remember that, you see, because I did treat the numbers as a variable. Now I get 18 and 48, which is my A and B, right? So then I can rewrite this one to be 3 times 18 plus minus 1 times 48. And over here, my A was 48, my B was 18, right? And my goal was to find some formula such as, R times A plus S times B equals to the GCD of A and B, right? So I was looking for some R times 48 plus some S time, we write it in a better way, 48R plus 18S should equal to 6, because the GCD of this two equal to that. So guess what I found? I found that 3 times 18, which this one is my S, and minus 1 is my R. If I do this multiplication, the result would become 6. And therefore, I found this R and S for the purpose that I was looking for. One small example before you go to your break time. So you will see that why this is very important for us. So as I said, we want to find multiplicative inverses. So remember for 15 and 8, so I said 1 times 8 plus 7. So I said 8 equals to 1 times 7 plus 1. So now I can start to work on this one. So I said that 1 equals to this one, right? 1 equals to 8 minus 1 times 7. 7, I can rewrite it based on this equation. I can say this equals to 8 minus 1 time 15 minus 1 times 8, right? So I can rewrite this. I can rewrite this to have 8 plus minus 15 plus 1 times 8, right? So if I get a factor from 8, I get 2 times 8 plus minus 15. That would be the result, right? So my S is this one. This is my R. And if you see this one, 2 times 8 minus 15, the result is always 1, right? 16 minus 15. And this is going to be my multiplicative inverse. Remember, multiplicative inverse of any number, A times some, B should becomes 1, right? So if you're working with the values, so 5, the multiplicative inverse of 5 is 1 over 5, so the result is 1. But over we are talking about multiplicative inverses, so I'm interested to find the multiplicative inverse of 8, which is represented as 8 to the power minus 1. This means that the multiplicative inverse of 8 mod 15. I'm looking to this value, and the result is going to be 2, because if I do 2 times 8, the result is going to be 1 mod 15, right? Because 2 times 8 is 16. The remainder to 15 is 1. So that's how we find the multiplicative inverses in modular arithmetic. We would just use the extended Euclidean algorithm. We would just write down the equations. It's a little bit tedious after you practice this for different numbers for yourself. You will find it to be very easy. But in the beginning, to just get the rhythm of it, it would just take some time. But I think with the examples that I provided for you, it shouldn't be very difficult. All right, I think we have break time. So let's have a break time for 10 minutes, and then we will come back.